Hello, I'm Justin. Today I'll be going over ICC4, which discusses using analog I/O pins and UART in PSOC. Now, the first thing that you'll want for this assignment is to, download and install the PuTTY terminal program. You can watch this video too, but I'll be going over most of what you need. PuTTY specifically allows you to um, see the printout of the UART visually on your computer. So it just lets you pull up a console and not this, here it is. It just lets you pull up a console and see what you're printing to the USART or UART. After you install PuTTY, you just need to build this circuit on your PSOC. And I'll show you what that looks like in just a second. So for this circuit, all you'll need is a potentiometer with 3 legs connected into 5 volts, ground, and an analog pin of your choice. Mine is connected to pin 3-1 in the analog pins. And now let's go over the top design and we'll go over some of the code as well. So for the top design, all you'll need is a UART and an ADC block. The ADC will convert analog signals to digital signals so that you can more easily read out digital signals to PuTTY. The UART is just used to send data like print out strings and print out the data onto PuTTY. For the ADC, all you need is one pin. This will be the potentiometer pin. It should just look like this. You shouldn't have to change much. The ADC should look like this. Again, you shouldn't have to change anything, but if you do, I'll leave this up for a second so you can. For the UART, again, it basically comes already prepared for what we're going to be using it for. Don't have to change much. RX and TX pins, I'll show you how to find on your PSOC itself in just a second. Let's go to the pins now. So pin 1, like I said, it's the potentiometer connected to port 3-1. You just have to make sure it's connected to an analog port on the PSOC. For the RX and TX, I'll show you my circuit in a second and how I found the locations for them. I don't have them connected up because you don't really need to hook them up on the main board. I think you would if you were using just the BLE module, but it doesn't have any impact for this right now. Now on the board, to figure out where to connect your RX and TX, which direction here, right here, you can see that pin 1-4 connects to pin 12-7 for the RX, and for TX, pin 1-5 connects to pin 12-6 for the TX. So if you are using the BLE module or and you want to use UART, you would connect those 2 pins together for the TX, those 2 pins together for the RX to make it work and ensure that you have a working UART system. For this, you don't need to. It still works without it. Next, we'll go into the main. I'll discuss both how I found all of this, where you should look for it, and how it all works. So first, let's just look at an 8-bit byte. An 8-bit byte is just binary, eight little digits of binary that we'll be using for some of our code. Here's an example for a 16-bit or a 16-bit byte. It's just basically 2 of these connected to each other. I changed the second bit of it or the second byte, the second 8 bits of it to make it a little bit different. Byte upper nibble shift is defined as 0x04u because it's used to grab the first 4 bits in a byte. When you look at the first byte that we have, 01001 is the first 4, and 0x04 is used to grab these first 4. 0x08, on the other hand, is used for the 16-bit byte and is used to grab the first 8 digits of it. So it'll grab this whole byte from this. The lower nibble mask grabs the last four bits of the byte. So for the 8-bit, it'll just grab the 1101. And for the 16-bit byte, you use 0xFF to grab the lower 8 bits in the byte. So it'll grab these. Now to put that more into context, to follow along with the assignment, not this one, this is hardware orders. To follow along with this assignment, the goal is to to build a 2-byte hexadecimal or hex byte. Where is it? Yeah, we want to output the ADC value in a 2-byte hexadecimal format to the UART. Now to do that, there's a few things that we have to do. First, what I did was I made a function that could take a hex byte and um, send it to the UART, which would print it to PuTTY. And to use this, we need a byte. We need a hex byte, so that would be like 1001. And we also needed the UART hex array, which was filled with the values that could be printed in the hex. So a hex, for example, would look like 0x3a, and this just means 0x3, 3 we would get it from here, a we would get it from here. The letters are in place of 2-digit numbers, so a would be 10, b is 11, c's and 12 and so on. And so what we need to do is translate 1001 into this first value for this first put char. To do that, what we do is we take in the byte of or the byte of bits. So this would be the first four if we're talking about the 3. And we want to translate it to, or we want to take the upper nibble shift, which right here is it would get us the first 4 byte or bits in the byte, and we want to compare it to the provided um, byte that we are putting into the function. So what we're saying is, say we're putting in 1001, that's what would go here, and we would compare it to 0x04, and this would tell the function, hey, we're giving you um, the first 4 bits in the byte, and uh, we want you to translate it in this format. So we're giving it 1001, and it would translate it into whichever value it is here. We do that again in the line below, but we're taking the lower 4 in the 0x3a, so that would give us the a, and or the thing in position in this second position. For the example, it's an a, but for us it would be 1101. So we're giving it 1101, telling it, hey, this is the second or the bottom 4 bits in the byte. Can you translate it into whatever that is here? The put hex int is where we are putting in the full 16-bit byte right here, and we are saying, hey, for the first 8, we want you to take the first 8 bits in the byte and do this function. And for this one, it's, hey, take the lower 8 bits in the byte, which is these, and telling it, hey, do this above function for that. And what this does is it would give us something, let me just write it here, it would give us something like 0x3a, and then let's say the bottom 8 would give us like 4B. So this is what the output would look like when giving it a 16-bit byte, and it separates it into top 8, bottom 8, which then separates it into top 4, bottom 4, top 4, bottom 4 of the others. And in the end, it would print out like this. For the actual code for the whole thing, we don't have to do that much. It's mostly just, hey, make a variable for the integer that we're grabbing, start the UART. We commented out, or I commented out, initialize the UART, because if you look at the functions that were given for the UART, let me go up here, should be here, yeah, UART start. If it's not initialized, then it initializes it when you use this function. So you don't have to initialize it yourself, because when you use start function, it'll initialize it for you. And the place that I just was put char. The way that I knew to do put char is because in the location right here, in the UART file that's provided, they give us a whole file full of functions that we can use with UART, and simply the one that I used is put char. What this does is it just transmits any byte of data to, or through the UART to PuTTY in our case, and that's all there really is to it. I would say a good place to look if you don't know how to do a certain thing is look in the .c files, because they oftentimes have a lot of useful functions that you can use, and they also explain how to use them. So definitely give them a look if you're lost and don't know how to do certain things. Now, look, going back to the main code, start the UART. We want to start the ADC. It does much the same thing. That's why I commented out initialize. I want to put string. This is another function that, again, I found in the C file. It just sends a string straight to the PSOC, and right now it's sending my initials, and then it's returning, which what this does is it tells the UART, hey, I'm done with that. I'm ready for another line. /n starts a new line underneath it. So the next string or the next char that you put to through the UART, it'll start on a new line. ADC start convert and ADC is end conversion are both very important as well. Also found in the .c is end conversion. What it does is it takes in either return status or wait for result, and these will tell the ADC or tell the PSOC, hey, I'm done sending you this piece of data, and I'm going to send you another one soon. It's just saying, I'm finished with what I just did, so you can do with that what you will. The other one, ADC start convert, what that does is it basically all it does is, let's see, starts the conversion process, runs continuously, triggered mode. It all it does is it converts analog values to digital values. So in our case, it changes whatever the potentiometer is sending in to binary, which we're then using to turn into hexadecimal. Next, for the for loop, all you're doing is, again, putting a string saying this is my ADC value, putting a slight delay, and then we are setting tx hex int, which is what we're using to carry the binary value that we're given. We're storing get result 16. What this does is it grabs the value that the ADC converter is sending out through its channel 0, which for us that would be giving us whatever the potentiometer is sending out in binary. We're setting tx hex int to that. We're using tx put hex int, which is this. And what this does, again, like I explained earlier, it changes the long 16-bit into two 8-bits, and it changes those two 8-bits into two 4-bits, and then it converts those into the 0x something something, and this will, when all put together, print out a 0x something 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 something. In our example, it's just 3a 4b. And this hexint, just for a refresh, is a representation of the ADC value in terms of hexadecimal, which is what is asked for in, sorry, not that one again, in this. It's looking for that 2-byte hexadecimal, which is exactly what we are sending it. You can use sprintf. We don't really need to. Output a carriage return. We do that because that's the /r and /n. Compile, download, and run the code. So now that we have all our code, which should print a hexadecimal value to our putty, what we can do is simply run the code, build it, and then verify with putty to see if it works as we expect it to. And it's looking like it is printing out a hexadecimal value. Obviously, if you turn the potentiometer, it changes. And that's really all there is to it for this assignment. However, I'm not a huge fan of this assignment because it's hard to work with hexadecimal, especially like when coding and for beginners. So that's why I don't like using this format for demonstrating that you know how to use an ADC converter. What I like instead, which is also much simpler, is simply asking it I'll show you the result first and then I'll explain how to get the result. So instead of using that kind of hexadecimal, I would rather see more easy to comprehend values, which obviously if the potentiometer is turned to 0, it outputs 0. When it's turned all the way up, it pushes out whatever its maximum is. For me, that's 2351 or 2350. It varies very slightly. But these values are a lot easier for beginners to understand and code around and put interrupts for. And if you're interested in coding for that and printing that, it's pretty easy. All you need to do is, again, set up the UART, set up the ADC, much the same. All the pins, also the same as before. The only thing that changes is there's a lot less code. What we're doing is we are just making an array of chars, which because C doesn't allow us to, or PSOC doesn't allow us to have a string. Like you can't just say string strings is equal to that. That just doesn't work. It doesn't like strings at all. So what you have to do is you have to assign a string or a char array, which acts like a string. I just made it this big because no real reason. It just gives a lot of room if I'm printing something very big. Once again, you want to start the UART, you want to start the ADC, and then you want to put string, my USART is so cool, /r/n. This is just showing, hey, it's printing at the very start. You want to start convert, much like before. No, I could actually move this. I'll leave it, whatever, it works. You want to get the ADC result, which, much like before, I have ADC val. In the other one it's called tx hex int, but in this it's easier just because I want to print the straight ADC val but converted into a more easy to read form. So I'm just setting ADC val as a uint, and then I am setting that uint as the result from the ADC converter. I'm then printing ADC value and the ADC value. I'm just no no shenanigans. There's no uh, functions that you have to make. Simply you just print the ADC value. And then I also put the time, and then I put or sprintf. This is actually really useful to know. Sprintf, it doesn't print to the putty or to USART. What it does is it converts the ADC val, which is right now a uint. It converts that into this format. It'll put it in the %d slot. So now strings, the array that I made previously, which is strings with a size of 50, strings will now print out ADC value and then the value plus the return and the new line. So now what we do is we put string time, which I got rid of for simplicity, so we don't really need that. And then we also put strings, which is what we set right above. And if we build this, it should just print exactly what I had up previously. Just wait for that to load, and it should be good. You can see it printed. JHUSART is so cool. And then it's printing ADC value colon the ADC value, which, like I said before, is simply ADC value, ADC value. That's what I made in the sprintf. And I think that this is a bit simpler of a kind of code to use to understand and utilize whatever um, whatever analog value you're trying to work with, because working with hexens can be a little difficult. Um, but that should fulfill everything we need, because we demonstrated our solution to reading the analog value, outputting it to PuTTY, where you see the ADC value change when you turn the potentiometer. I showed you two ways to do it, with the hexent, which is what this specifically wants, and with what I think is an easier to comprehend straight value. I hope that was helpful for you, and I'll see you next time.